Hi, today we're going to talk about resistors. Let's start with a simple resistor circuit. Something needs to supply the oomph to make our circuit go. A battery or variable voltage supply. We need something that allows charge to move freely through the circuit. Copper wires work nicely. And of course, it's a resistor circuit, so we need resistors. Let's focus on carbon film resistors. Aren't they colorful? Resistors allow current through, but not for free. There's an energy cost. Resistance R is quantified by the volts needed to push through a unit of current. It's V over I. The unit for resistance is ohm, which is represented by the capital Greek letter omega. An ohm is a volt of potential difference divided by an amp of current. When the ratio R is constant for different current voltage combinations, we say that the resistor obeys Ohm's law. V equals IR, where R is constant. If you know any two of the quantities, you can solve for the third by multiplying or dividing. And here is a fun way to visualize Ohm's law. Potential difference, volts, provide the push. Amps are being pushed, and ohms are making it difficult. Not all resistors obey Ohm's law. For example, the ratio R is not constant for light bulbs. Examine the V versus I graph for a miniature light bulb. Yes, this is actual student data, and it's not linear. V does not equal I times R. In contrast, check out the V versus I graph for a 300 ohm carbon film resistor. Again, this is student data. Performing a linear regression on the data, the slope is essentially 300 ohms and the intercept is about 0. Carbon film resistors obey Ohm's law. Let's take a look at this resistor. There are 4 color stripes: orange, black, brown, and gold. What do these colors tell us? The first 2 colors represent digits. In the sample, yellow stands for 4, violet for 7. So we start with 47. The third color represents a multiplier. We multiply by a power of 10. Black is 10 to the 0th, so multiply by 1. Brown is 10 to the 1st, multiply by 10. Let's see, down the column, green, multiply by 10 to the 5th, which is 100,000, or 100 kiloohms. For our example, the third stripe is brown, so multiply by 10. This is 470 ohms, at least nominally. The fourth color tells us about tolerance. Silver band resistors are supposed to be within 10% of that nominal value. Gold band resistors within 5%. Red band within 2%, etc. So this resistor is supposed to be plus or minus 5% of 470 ohms. Plus or minus 5%. Okay, 95% of 470 is 446.5 ohms. 105% is 493.5 ohms. According to the manufacturer, R is supposed to be between those two numbers, 446.5 and 493.5. Back to our orange, black, brown, gold resistor. Orange, black, 30. Brown means times 10, so we have 300. Gold says it's 300 plus or minus 5%. Adding resistors end to end is like adding hurdles in a hurdle race. More hurdles does not make the race easier for the hurdler. And more resistors does not make it easier for charge to move through the circuit. Connect two resistors, R1 and R2, in series. What is the equivalent resistance of the combination? Well, with more hurdles, we can be sure that the equivalent resistance is greater than either R1 or R2 individually. The same current I flows through both resistors. V1, the voltage drop across R1, is R1 times I. V2 is R2 times I. The battery supplies the voltage drop across both V. So V is the sum V1 plus V2. The equivalent resistance is the applied voltage V divided by the current I. The takeaway here is, in series, add up the resistances. Adding resistors in parallel is like opening up more pipes. More pipes exiting the tank means it's easier for water to flow out. And more resistors in parallel mean more paths for current to flow through. Connect two resistors, R1 and R2, in parallel. What is the equivalent resistance of the combination? Well, with more pipes, we can be sure that the equivalent resistance is less than either R1 or R2 individually. Both resistors have a voltage drop of V, but the total current, I, splits into two parts. I1 flows through R1 and I2 through R2. The total current I is the sum of I1 and I2. Current I through a resistor is the voltage over the resistance, and the total current is V over the equivalent resistance of the combination. Cancel the V's and we see that the reciprocal of the equivalent resistance is the sum of the reciprocals of the individual resistances. Let's summarize our resistance equations. We have Ohm's law, V equals IR. When resistors are connected in series, add to find the equivalent resistance of the combination. If they all have the same resistance, say R, the equivalent is the number of resistors, N, times R. When resistors are connected in parallel, the reciprocal of the equivalent resistance is the sum of the reciprocals. If they all have the same resistance, R, then we have 1 over the equivalent resistance equal to 1 over R plus 1 over R, in fact, N over R. So R equivalent is the reciprocal of that, R over N. Let's do an example. The resistor values are given in ohms. We're supposed to find the equivalent resistance of the circuit. Start with the innermost parallel section. 2 10s in parallel. That's 10 over 2 equals 5 ohms. Combine any resistances in a branch. So let's start with the right branch. There is a 20 and a 5 in series. 20 plus 5 makes 25 ohms. Next, in the middle branch, there's a 30 and a 20 in series. 30 plus 20 makes 50 ohms. Now, the 50 and 25 branches are connected in parallel. The reciprocal of R equivalent is the sum of 1 over 50 plus 1 over 25. That's 1 over 50 plus 2 over 50, so it equals 3 over 50. The equivalent resistance, then, is 50 over 3 ohms. Finally, there's a 20 connected to the 50 over 3 section and then to the 15, all in series. The equivalent resistance of the entire circuit is 20 plus 50 over 3 plus 15, which is about 51.7 ohms. What can we do with that number? Well, one thing we can do is, if we know the voltage supplied to the circuit, we can calculate the current. Suppose the battery supplies 10 volts to the circuit. Now we can calculate the total current. I equals V over R equals 10 divided by 51.7 equals 0.19 amps. That's all for now, folks.